So the next speaker is Professor David Lowe, who is a professor of computer science and director of information and system cluster at School of Computing and Information Systems, Singapore Management University in Singapore. So his research is in the intersection of software engineering, cybersecurity, data science, which encompassing social technical aspects and analysis of different kinds of software artifacts with the goal of improving software quality, security, and developer productivity. So his work has been supported by NRF, MOE, NCI, and AI Singapore, and various kind of international research projects. So he has won numerous international research service awards, as well as best paper awards. So he's an IEEE fellow, fellow of automated software engineering, and ACM fellow. So please.
Thank you very much, Jack, for a very nice introduction. A very good afternoon to everyone. So I'm very happy to be able to share this talk entitled Testing the Limits. So what breaks and how we can partially fix this large language model when we apply it to automated software engineering. So as we have heard many times today, people have been looking into large language models a lot, and there is like exponential growth in the large language models. And in our group in Singapore, we have started to look at it when it was still called the pre-trained transformer model. And then at that time, we start looking into how pre-trained transformer model in 2020 can be applied to a number of software engineering tasks. And we have demonstrated that it's actually performed very well as compared to other deep learning approaches and as compared to the traditional machine learning. And so we are very excited, and since 2020, we have actually moved towards investigating how we can use this large language model for different software engineering tasks. And of course, there are many excellent work out there, and recently we set out to do a survey about the many different works, excellent works on this area of large language model for software engineering. And actually, indeed, there is a huge exponential growth along the years. So from 2020 all the way to 2023, you can see this exponential growth. And when we do this study, actually, it's at the mid of 2023. And even at that time, the number of papers that were published in 2023 is much more than the number of papers in 2022. And we also see that how large language model has been applied, not just on one part of software engineering activity, but actually across different software engineering activities. Of course, the most of them is on software development, and a minority is on software design, right? But there is increasing numbers of papers in these different aspects of software development. So in the last 2 years, we set to look into the limits of this large language model for software engineering. So why do we want to look at the limits? Well, we want to look at the limits because once we know the limitations of this large language model for automated software engineering, we know what to improve. We know what we need to do to carry this work forward. And actually, there is several very exciting talks earlier, I think by IPEC, and also highlighted earlier by Tom, that trust is very important. And it's important for us to have the right calibration of trust. And in order to have the right calibration of trust, so one thing we want to do is that we need to know the limits. And then we know to what extent we can trust this large language model for automated software engineering. So in the last few years, we have investigated 2 different dimensions to identify what things are broken when we apply large language models to the limit, right? And one dimension is on the data dimension. And we look into different things. For example, how much large language model can perform when the data follow a long-tail distribution. We also look into the evolution of the data. We also look into security of large language model, for example, backdoor, and also feedback poisoning. Another thing that we look at is on the model itself. Like the large language model is huge. It consumes a lot of energy. There is size and latency problem. I think Hiro has highlighted earlier today that this actually is a sustainability issue as well, consume a lot of energy. So we look into ways to address this problem as well. Of course, there's also the problem of hallucination. I think Emad has highlighted earlier, robustness, and so on. And we look also at problems in the intersection of these 2 different dimensions. So I only have like a few minutes here, so I'm just going to talk more about these two different problems that we have found in our recent work. One is on long-tail data, another one is on data evolution. So long-tail data. So we have this work that was presented just a few months ago in Luxembourg. So the title is "The Devil is in the Tails," and then how these long-tailed code distributions can impact this large language model. So the research question that we seek to answer is this one. So how does large language model for automated software engineering perform on long-tailed data? Does software engineering data follow a long-tail distribution? Yes, they do. So the first part of our research is to confirm this. So we look into 3 different tasks: API sequence recommendation, code revision recommendation, vulnerability type prediction, and all of them follow this long-tail distribution. For example, in terms of the vulnerability type, just the top 5% of the vulnerability types actually occupy half of the data samples. So does this create a problem, this long-tail distribution? So what we seek to answer this question, what we do is that we take a training data set, and then we use it to fine-tune a large language model. And then we take a test data set, and we break it into 2. So we take the head part and then the tail part. And we simply put the head part to this large language model and the tail part to this large language model, and then we compare the performances of this large language model on the head part and the tail part of the data. And this is the summary of our findings. So we have many bar charts here corresponding to 3 different tasks: API sequence recommendation, code revision recommendation, and also vulnerability type prediction. So the blue bar here corresponds to the performance of the large language model on the head data, and the red part is on the tail data. So you can see there is a big difference. So the difference is between 30% even to 200%. So this indeed is a problem. So often the news we may hear of the successes when they are applied on the head data, but on the tail data, the story can be very different. And please remember that the tail data can be very long. So we hypothesize that this can happen because fine-tuning can be biased by the frequent head data. And can we do something about it? So what we did is that we look into research done in the machine learning literature. For example, we look into the focal loss method, long-tail recognition via weight balancing, recently proposed methods. And then we want to see to what extent they can help in dealing with this problem. And this is our findings. So we find that the one that are highlighted with the green arrow means there is an improvement. The one that has the red arrow means there is a reduced performance. And we see that by applying this FL and LTR method, there is some increase in performance, but the increase in the performance is rather small. So there is a need to look more into this long-tail distribution and develop effective methods to deal with it. And the next thing that we look at is on the evolution of data. So I'd like to argue that software engineering data is the one that evolved one of the fastest pace in terms of evolution. And we seek to understand to what extent we can adapt this large language model to deal with this fast pace of software evolution. And then in software engineering, we often see new libraries. And even if we have an existing libraries, the developer often deprecate old APIs and create new APIs. And also new programming language that are getting more popular over time. So how do we adapt this large language model so that they can make sense of this whole new data? Well, one way to do that is that we can fine-tune this large language model with this new data. But does it have any negative consequence? Well, there is this problem referred to as catastrophic forgetting. So large language model is like us humans. When we acquire new knowledge, sometimes we forget the old knowledge that we used to retain. For example, I've forgotten all the chemistry and biology I learned from high school. So does this catastrophic forgetting happen? To what extent does it happen? Does it influence this large language model when it is applied to automated software engineering tasks? So that is the question that we seek to answer through this study. And what we did is as follows. So we create 5 different out-of-distribution data sets. So these data sets are disjoint, right? And one is called general, the other one is security, another one is Android, another one is web, another one is Guava. And then what we do next is that we use one set of the data to fine-tune the model. And then we also employ this continual fine-tuning, meaning that we take one data set, let's say general, fine-tune the model, take another data set, for example, security, fine-tune the model, and we continue to do that. And what we need to do next is just we need to compare the two and then see to what extent this large language model forget a particular domain, for example, the security domain, due to this continual fine-tuning with possibly new data. So we try on a number of tasks, including API usage prediction, given a particular location, predict what API should be used there and how to use the API. And this is the summary of our findings. So if we just use security data to fine-tune the model, and then we take a disjoint test set to test that large language model that we have fine-tuned, we can actually get a 40% exact match score. However, if we continually fine-tune that large language model with other kinds of data, there is forgetting happens. And the drop in performance can be up to 55% as compared to the original results. So are there mitigation strategies available out there? So we look into the machine learning literature, and we find a number of strategies. The more advanced one is to add some regularization term so that we can prevent this catastrophic forgetting by penalizing changes to important neural network parameters. So these include the study 31, 66, 9 in our paper, and there are also some more traditional and simpler approach. For example, rather than forgetting all the old data, maybe we can sample some of the old data, put it together with the new data, and use the whole collection to fine-tune the model again. So another possibility that is performing the best here is that let's just use all the data that we have collected so far and then fine-tune using all the data. However, that will be very expensive. That may not be practical. Right? But in any case, these methods can help to reduce catastrophic forgetting. There is still a gap there, and a lot of research are needed, I think, to push this forward when we need to deal with data evolution. Right, so these are the two studies that I like to highlight. There are many other limitations of large language model for automated software engineering. If you're interested on them, please refer to some of the papers, some of the QR code I highlighted here. And if you're attending ICSE 2024 in Portugal, so two of them will be presented there, and we're looking forward for your inputs and comments on those work as well, if you attend the conference. And recently, we are looking into limits, and we consider limits as, for example, could we go beyond accuracy? Many of the studies focus on the accuracy of large language model. Could we go beyond it? Another thing that we want to look at is going beyond the common cases. What happened to the long-tail distribution? Another one that we want to look at is looking beyond just one snapshot of the data. Data evolved. So what is the performance of large language model when this data evolves? So related to the first one, we have also recently done a survey of works that have looked beyond accuracy. For example, works that look into robustness, security, privacy, explainability, efficiency, and usability of these large language models when they are applied to software engineering tasks. So we just released this archive paper a few days ago. We are looking for inputs and comments. If you have inputs and comments, please share it with us. And in our study, we have also shown there is an exponential increase in the number of such publications, and people have looked into different aspects, not just accuracy, but also robustness, security, usability, and so on. I believe I still have about 4 minutes, and I'm going to talk a little bit about what I think would be the road ahead. So I think today we have known a little bit about this beast called large language model, especially when we apply it to automated software engineering. There are many things that we do not know. There are many things that are unknown, and we want to seek to further find out the limits of this large language model, especially when applied to different software engineering activities. And I think sometimes we also need to provide a little bit of pressure to see where else this large language model breaks. For example, earlier there is, I think, very nice discussion, between Ahmed and many other speakers earlier, where basically talks about, for example, how about the performance of large language model for a particular domain? So let's say we take one domain, let's say the development of drones, right? The software that runs on drones. Does large language model work for that kind of development? I think there is more work that can be done to investigate this. And I think Ahmed earlier today has also highlighted that people have been focusing a lot on this large language model, but people are moving towards vision language model, right? So I think we also can use multiple large language models, multiple foundation models. Each of them are not perfect, but maybe we can stack them together so that the weaknesses of one can be addressed by the strength of the others. And just to illustrate this picture that I highlighted earlier, actually I make use of a number of foundation models. First, I asked ChatGPT, what is a good picture to use for illustration? ChatGPT gave a few suggestions. And then I create the base image using this Microsoft Bing image creator. And then AI tool, an API from OpenAI, refine it further. Finally, it doesn't get it right. It cannot put the text on the fabric over there. And then I need to use Photoshop to add that particular text. So I think in software engineering as well, why limit ourselves to just one large language model? We can use multiple of them. And in XC 2024, actually, this is one work that we'll present soon. We actually highlight that we can make use of multiple LLMs. I think, as Ahmed also mentioned, the bigger LLM may not be the best, so bigger may not be better. And we highlighted that how a small LLM can work together with a big LLM to deal with this problem, vulnerability repair. And with certain kind of data-centric innovation, we can double the efficacy of the previous method. So another thing that I think is also important, as also highlighted by many previous speakers, is that we want to look on human-centric large language model for automated software engineering. Right? This importance of trust is there. There's also this importance of synergy, right? So if a developer does not trust a tool, developer will not use it. If a developer cannot synergize with a tool, then the developer will not use it. So I was asked to write a thought about this that appears in the Future of SE in XC 2023. If you are interested, please read this paper. It is available also on archive. So I think we live in an exciting time. So I feel like maybe we are going back to the 1900s for the aeronautics. So at that time, in the 1900s, there is this picture there. These are the Wright brothers. This is the first flight. Do you know how long that flight lasted? Was it 20 minutes? 2 minutes? 20 seconds? Well, it's actually just 12 seconds. But it's a breakthrough. That's the beginning, right, of an era, so that all of us can travel here using airplanes. So similarly today, I think FM plus SC, maybe there are still a number of issues that we need to resolve, but together, as a whole community, when we work together, I think we can do great things. We can transform how software engineering will be done in the future. So with that, I would like to thank and acknowledge many members and collaborators for the work that I presented here as part of the Center for Research of Intelligent Software Engineering. So thank you for your attention. Happy to answer questions at the end during the discussion section. Thank you very much.
So thanks, David, for the wonderful talk.